Okay, sir. Thank you so much, sir.
Dear participant, please be seated. The session is going to be held within few minutes. like to invite Dr. P. Shanti, Assistant Professor, PG and Research Department of Mathematics, SFRC, to deliver the chief guest introduction.
A warm welcome to everyone for this session. It's a great pleasure for me to introduce our resource person, Dr. Sunil Mathew, Associate Professor, Department of Mathematics, National Institute of Technology, Calicut, Kerala, for this online session of two-day international conference on mathematical challenges and novel applications, ICOMACNA 2024, jointly organized by the Sister Papers, Rajaratnam College for Women, Sivagasi, Ayya, Nadar, Janaki, Ammal College, Sivagasi, and Rapo Institute of Technology, Rajaratnam. First of all, I would like to register my gratitude towards our resource person for accepting our invitation and to deliver a speech on the topic iterated function systems and fractals. Thank you, sir. He has completed UG, PG and PhD research in Calicut University, Kerala. He entered into the teaching field in the year 1999 as a visiting faculty, then guest lecturer ad hoc assistant professor, and now promoted as associate professor with a total teaching experience of 25 years service. He had so far published 120 research articles in reputed international journals, indexed ACI and Scopus. I wish to mention a few of his recent publications: Macro-Minkle Theorem for Directed Fuzzy Incidence Networks and Connectivity of Directed Fuzzy Incidence Graph applied to traffic networks. Also, he published research articles in many conference proceedings. Sir's academic contributions extended as editor in 4 international journals and a reviewer of more than 50 journals in IEEE, Elsevier, Springer, Whitey and World Scientific. He is a life member of the professional bodies like Kerala Mathematical Association, Ramanujan Mathematical Society and other bodies. His area of interest and expertise are biocomputational modeling, cancer detection research, fractals and chaos, and fuzzy graph theory. He published 10 books and 1 book chapter. In addition to his credit, he received the award, Indian President Award for the Best Scout in 1992. He delivered more than 58 invited talks at various conferences and workshops. The recent projects currently he is working on fuzzy graph clustering funded by Department of Atomic Energy, Government of India, fuzzy networks funded by University Grant Commission, Government of India, and applications of partial cut sets in weighted graphs funded by NIT Calicut. I am proud to introduce such an eminent person to this session. With this brief note, I hand over the session to our resource person. I eager to hear from you, sir. Thank you.
Thank you, ma'am. Now I would like to welcome our respected speaker, Dr. Sunil Mathew, Associate Professor, Department of Mathematics, National Institute of Technology, Calicut, Kerala, to deliver their presentation. Over to you, sir.
So, thank you very much. Can you hear me?
Yes, sir.
Thank you. Okay. Ellavarukkum vanakkam. First of all, I would like to thank all the faculty members of ANJAC College for giving me an invitation to your international conference. Okay. Generally, I like to talk to my audience, face to face. Because, talking to a computer will never create any sort of interest either in the audience or in the speaker. But unfortunately, due to some unavoidable circumstances, This time, we converted to online mode. So hope you will conduct another event in future and call me. I will come there and meet all of you in person. Okay. So I'm directly going to the topic as well as to the presentation now. First of all, I think my screen is visible. If it is not visible, please let me know. You can see it is visible, right?
Yes, sir.
Okay, good. So in the screen, you may be seeing a picture. Actually, if we were talking face to face, I would have asked you what you are seeing or what you are looking at. Actually, the picture you are seeing is that of the universe. Recently, in the year 2022, a new telescope called James Webb Telescope was launched into the space. And I will show you the picture of the telescope. This is the picture of the telescope. This telescope is now resting at a distance of 15 lakh kilometers away from Earth. And this is a mathematical adventure. We can call it as a mathematical adventure or a mathematical, as mathematical, what we cannot call anything because it is a mathematical fantasy. See, this telescope is sitting at a point in space. Look at this picture. This picture is showing three spatial objects. This is sun, this is earth, and this is moon. So this telescope is now taking rest at this point. This point is called second Lagrange point. Actually, there are several Lagrange points, L3, L4, L1, L5. There are 5 Lagrange points here. A mathematician, as all of you know, Lagrange is a very famous mathematician. He solved a 3-body problem. 3-body problem means sun, earth, moon body problem. And that problem, if you Google it, you can find it as a big mathematical problem. Lagrange solved it. The problem is, see, suppose your telescope is near sun, what will happen? Sun will swallow the telescope in time. If it is earth, due to the gravity of earth, it will fall into earth after some time. Then also there is a possibility. So, is there a point in the space where these 3 bodies have no effect? If you place an object at this point, L3, L1, L4, or whatever, whichever it is, the action of these 3 bodies are irrelevant. Nothing will happen. This James Webb telescope will move in time forever without the action of any 3 of these bodies. That is what is the 3-body problem. So this is the telescope sitting maximum distance from Earth now. This is a mathematical, what we say, a super invention. There are a lot of math involved in this. But today, and of course, I will show you some of the pictures taken by that telescope. See, you will wonder by looking at the pictures. Look at this. This is not a picture drawn. This is a real picture. This is a star explosion. These are all galaxies. What you are seeing nearby are galaxies. See, another picture is this. This is also a nebula. Okay, a star is exploding. New stars are, new stars born in the neighborhood. So the such things, places are called nebulas. Look at this. These are all galaxies like our galaxy. Our galaxy, it is Milky Way. Milky Way may be somewhere here. Since we are taking this photograph from Milky Way, you cannot find a Milky Way here. See what this picture shows: the superposition of or merging of three different galaxies. Anyway, you cannot imagine or you cannot believe this at once. And this happens in huge distances, light years across, not kilometers. As you know, we are nothing. We human beings, we Earth, we solar system, we Milky Way is nothing. See, and in future, our galaxy will merge with some other galaxies. So we don't know what is happening outside. See, this picture itself, when we take in high clarity, see, as is objects deep. So mathematically, this object has several properties. Okay, look at, okay, these are all similar pictures taken by that space telescope. This picture was, this picture is called Hubble's deep space. Actually, we had even now it is working, telescope called Hubble telescope that is also outside the environment of the Earth. That is also looking into deep space. One day we zoomed that mirror to a 1 millimeter into 1 millimeter square image window, and we captured not this image, a similar image. In the previous year, James Webb also, zoomed in 1 by 1 millimeter and he captured this image. These are all galaxies. Actually, mathematically, this is a dynamical system. I don't know how many of you have heard about it. There are so many things which we cannot explain. You see, look at certain portions. This portion and this portion are similar. Some of them are reflections. So when you look at the sky, you are not seeing a hello. Is it okay?
Okay, sir.
Okay, thank you. Yeah. So fractal geometry is the study of natural shapes. Or we can say fractal geometry is the geometry of nature. Okay. So there is a major difference between Euclidean geometry and fractal geometry. We have studied 3D geometry, 2D geometry, 1D geometry, etc. We studied circles, cylinders, spheres, etc. They are all coming in Euclidean geometry, where we study simple, smooth, predictable curves. Okay? But in nature, curves are very complex. Look at the curves on the right-hand side. The curve over the boundary of a leaf is really complex. And actually, they are nowhere smooth. Smooth means differentiable. See, no point on the boundary of a leaf is differentiable. No point here is differentiable. So, but for a parabola or an ellipse, every point is smooth. That means there is a unique tangent at that point. Whereas, if you look at a point in the boundary of this leaf, no point is differentiable. That is a major difference between a curve in Euclidean geometry and a curve in nature. Nowhere differentiable. Okay. So this type of nowhere differentiable boundary curves or this type of curves cannot be studied in Euclidean geometry. So that is the importance of fractals. So we are coming to fractals. These natural objects are called fractals. So this is the man who introduced the fractal geometry. And fractal geometry, I told you, deals with objects in nature. It was introduced by Benoit Mandelbrot in 1975. The meaning of the word fractal is fragmented or broken. And a fractal is characterized by some of this infinite data. I will explain these things one by one. See, when you studied analysis, you might have studied this nowhere differentiable function. Some of you, if there are PG students among you, might have seen this Weierstrass function, this summation. This is the first nowhere differentiable curve studied. I said fractals are nowhere differentiable. So you can say this is the first fractal we have studied or constructed. You have also studied this set, Cantor set. Even though it was invented in a different perspective, this one also is a fractal. I will tell you why after some time. This is another very famous curve called Koch curve. This is another example of a human-made fractal. We will explain how this becomes a fractal. Okay. And when we study fractals, there is a term called self-similarity. Okay? And the self-similarity occurs when we try to generate a fractal mathematically. That study was done by John E. Hutchinson in the year 1981. We will see what is the meaning of the word self-similarity. This is another major contributor in the field of fractal geometry, K.J. Faulkner. He introduced certain other kind of fractals called subsimilar and super self-similar fractals. We will see what they are. So let us proceed to the mathematics of fractals. Anyway, some of the definitions which I introduced in the beginning may be beyond the scope of a BSc student. Don't worry, if you are not sure or if you feel difficult, you may skip the definition. Actually, you might have seen measure, might have studied Hausdorff measure also. For the time being, I will skip few slides. I will tell you, like measure, length is a measure, area is a measure, volume is a measure. So there is a measure called Hausdorff measure. We will discuss it after some time. It's a very general terminology. When we come to R3 or R2, there is an easy way of computing Hausdorff measure. I'll tell you what is that. That may be better, I think. Okay. Because, anyway, I'm skipping few slides. Hausdorff measure of closed interval 0 to is 2. For classical sets, Hausdorff measure is nothing but the ordinary measure. For an interval, it is the length. For an area, it is the area, etc., etc. Now, I'm skipping Hausdorff-Besicovitch also. Anyway, why I need this is a fractal is defined as an object whose Hausdorff dimension is strictly greater than its topological dimension. We will come to Hausdorff dimension after some time. Look at this dimension, topological dimension. That is a very simple concept. You just cover this curve by bolts. Look at this picture. I covered the line segment, not a straight line segment. See, with some bolts. They are the open bolts of the plane. You can delete some of them. You can delete some of the bolts and you may get a refinement of that. This is it. Look at this. This is the minimum number of bolts required to cover this curve C. How many intersections are there? Maximum 2. 2 minus 1. That is what is called the topological dimension of an object. So if it is something which has no area, topological dimension will be 1. If it contains an area, topological dimension will be 2. If it contains a volume, topological becomes 3, etc. So this definition is needed, even though I didn't explain Hausdorff dimension. Fractals are set for which the Hausdorff dimension strictly exceeds its topological dimension. Actually, Hausdorff dimension is another dimension. I will tell you what exactly it is before we proceed further. If you have a straight line And this line, this is also a line. Even though this is not straight, if you pull at the end, you will get a straight line. See the way in which this particular curve fills the space and the straight line fills the space are different. Okay? The way in which, see, topological dimension of this is also 1, because when you take coverts, maximum intersection will be 2. So 2 minus 1 is 1. So a line segment and this curve both has topological dimension 1. But how they fill the other space, it is different. Suppose each and every point absorb oxygen. Your lungs, for example, contain so many bends and folds and all, because we want to absorb more oxygen. It is not like few papers folded together. If it was like few papers folded together, it cannot absorb air properly. So this one can absorb more air. If this is an antenna, you can absorb more signals than a straight line antenna. So straight line cannot fill the space properly, whereas this can fill more. So that feeling matters. That is what is this Hausdorff dimension. Look at the feeling. Feeling is 1.2618. But for a line segment, it is only 1. I told you Hausdorff dimension of any classical objects is the topological dimension itself. So here, it feels more than a straight line. So definition we will discuss later, but this is the essence of Hausdorff dimension. Now, generally, if somebody asks you which is a fractal, which is not a fractal, it is very difficult to identify using the definition, this definition. So what we want is some properties. Generally, a fractal is identified by means of its properties. So there are several properties. The first property is called self-similarity. Look at this picture. This picture is made by or composed of its own images. The big image shrinked, reduced the size, and going to this side in green, shrinked and going to this side in blue, shrinked and going to this side in red. Look at this. So mathematically, the entire set A equal to some F1 of A, union F2 of A, union F3 of A, etc. It is written as the union of its own images. That property is called self-similarity. Look at the pictures. Even though they are not completely self-similar, see this second leaf, the total leaf, you shrink the size, keep a smaller image here, another image here, another here, etc. And even in this, you can see again the same transformations are applied, going to the left side, left, right, in that manner. So it goes in infinite successions. So this is written in terms of its own copies. So second image is self-similar. Look at the tree. Actually, so many portions, look at this. The entire image is this. This is a shrinked image going to the right side, going to the left side. Again, shrink, go to left, go to right, shrink, go to left, go to right. That's the construction. So this is what is the self-similarity property. Okay. In nature, you can see self-similarity at many places. This is a broccoli. You may zoom a small area. You will get like this, self-similarity. This is nothing but, a large glacial lake. You might have seen the reservoirs of dams everywhere. If you take pictures from the sky, it will be looking like this. Look at the similarity of these positions. Even though it is not 100% self-similar, there are a lot of self-similar portions. Clouds, okay, and big trees. You can see the self-similarity. Sometimes, several portions will be the zoomed or shrinked copies of itself. Look at this. So the first property of is a fractal self-similarity. Second is infinite details. See, look at this picture. I'm going to take a small portion here and zoom it out. When you zoom, I'm getting again an infinite similar picture. You take another small picture from here, zoom. The same pattern will continue. So that is what is called infinite details. Look at this. See, if you take, this is something like a coastland. If you take a small portion and zoom, similar patterns, will continue. This is a length. Actually, it goes to infinity indeed, iterations to infinity. So you will have infinitely, if you zoom a portion, it will contain infinitely information. Again zoom, again zoom, again zoom, so that infinite information will continue. That is called second property, infinite details. Okay. Third property is infinite length. Actually, you take a leaf, this leaf. What is the length of this leaf? You may just think that it is a finite length. No. Actually, if you watch the boundary of this leaf with a microscope, you will find so many up and downs in the boundary. Boundary may be like Everest mountains. Up and downs can be found. And this distance, if you measure this distance by a 10 centimeter scale, you may get it as 20 centimeters total length. If you measure this with a 1 centimeter scale, you can measure more crook and bends, and that may be 20 centimeters. If you come with a one, I'll show you some other pictures better. This one, for example. If you measure the coastline with a 1 kilometer scale, 1 kilometer plus 1 kilometer plus 1 kilometer plus 1 kilometer, only 4 kilometers. If you measure the coastline with a 10 centimeter scale, you can measure more crooks and bends, and you will get 20 kilometers. If you measure this with the 1 nanometer scale, you may get as 40 kilometers. So as the length of the measuring device goes to 0, the length goes to infinity. That means the actual length is infinity. We cannot measure the length of a fractal curve. So this length is actually infinity. We can easily prove it mathematically. So that is the third property, infinite lengths. And next one is the definition itself. If most of the fractals, again I'm telling you, only most of the fractals possess fractional Hausdorff dimension. That feeling dimension will be 1.26 something. This is only for this particular curve. It will not be an integer dimension. So many cap properties: cell similarity, infinite details, infinite length, fractional dimension. If an object in this R3, a human being, a car, a chalk, a paper, they are all indeed fractals. So possess any of these properties, it is characterized or qualified as a fractal. Look at this. See, this picture is nothing but you just heat a rod, metal rod. Heat travels from, higher concentration to lower concentrations. So that will form a particular pattern. So diffusion will take place. This picture will be the resulting picture. This is a fractal picture. You can see cell similarity here. Okay. Anyway, I told you Hausdorff dimension is little difficult to measure because it is a difficult mathematical concept. But this picture is drawn in R2 in plane. So there is a technique to find the Hausdorff dimension of this picture. That technique is called box counting method. You just cover this image by boxes of size epsilon. Okay, boxes of size epsilon. Now you count how many non-empty boxes you have. Look at this. There's an empty box, like an empty box. Okay, so these are all non-empty boxes. These are all non-empty boxes. Repeat the same procedure for smaller and smaller and smaller epsilons. Okay, you just cut these unused boxes, right? So repeat this process with smaller and smaller and smaller epsilons. So number of non-empty boxes, you can consider it as some n of epsilon. In the limiting case, if the number of boxes is n and epsilon is that number bx epsilon radius of the ball, then the dimension in plane or in Hausdorff space can be taken as log n divided by log of 1 by epsilon. So this is a shortcut formula for finding the fractal dimension of an object in Rn. So this dimension is also called box counting dimension. But if you measure the box counting dimension of natural mathematical objects like area of an ellipse, you will get it as an integer because it can fill the entire space as its mother space. See, if you cover it by boxes and find n of epsilon and find that number, that will be 2 only. 2 is the dimension of the mother space. But for irregular, curvy, shrinked objects, that will be more, as it can fill the space more. Okay. Look at this. This object, topologically dimension is 1. Now, the length, if you take it as 3, sorry, 1, this is 1 by 3 length. So 1 by 3 length, when you use, you need 3 boxes to cover it. So log of 3 by log of 1 by 3. Here, when I use 1 by 9 length to cover this, I need 12 boxes. So log of 12 divided by log of 1 by 9. You continue it in that manner. So you can see the first case, log 3 by log 3 is 1. Second case, log 12 by log 9 is 1.13. This number sequence will converge to the limit 1.26168. This is what is the what is the box counting dimension of Koch curve, sometimes called Hausdorff dimension in Rn, R3, R2. Okay. So these are all certain very famous fractals. Those who are interested in fractal can search Cantor-Set, Hennen map, Koch-Snefflake, 2D Cantor dust, etc., etc. They all possess non-integer dimensions. Okay, so many are there. So I have already told you about Nadar differentiability. If you take a fractal curve or fractal surface, or any curve in this universe, actually, that qualifies. Any curve in this nature is nowhere differentiable. If you consider the branch of, this trunk of a tree, you draw a curve. You draw a curve in your own body. You may feel that it's a smooth curve. No. We are human beings, our eyes are very bad. That's why it looks like a smooth curve. Otherwise, when you zoom the curve, it will go down and up and down and up and down continuously, and no point is differentiable or smooth. So these are the properties of fractals. Self-similarity, infinite details, infinite length, fractional dimension, nowhere differentiability. This is a very, very famous fractal. This is called the Mandelbrot set. Okay? Very famous. See, this itself is worth studying in one lifetime. Actually, its boundary, I'll tell you what is that. It is topological dimension of the boundary is 1. Its Hausdorff dimension is 2. All the properties are sufficient only, not necessary. See, this one has Hausdorff dimension 2, not a non-integer number. But still, this one is self-similar boundary. That is why it is a fractal. So, before going to the next slide, I will show you one beautiful picture about this Mandelbrot set. You can see one video. Hope you can see this. I'll tell you how to produce this. As you zoom your Mandelbrot set in and in and in, you can find the pictures like this. Same Mandelbrot set can be found inside. Actually, this picture is obtained by iterating a complex function, f of z equal to z square plus c. When you put a complex number inside, its orbit can be found. F of z naught, f square of z naught, f cube of z naught, where that sequence go. If it goes to infinity, that will be in this white region. If it goes to 0 or bounded, that will be in the black region. So f of z equal to z square plus c, you don't worry about z square. What are the constants c? C is also a constant for which f of z square plus c is bounded. So it is simply set of points in a complex plane for which f of z equal to z square plus c has a bounded orbit. That's what is this. But this is a beautiful object. You search in the YouTube, you can see in the boundary of this object, you can see all the patterns in the universe. Even the patterns which you visualize in your dreams. Anyway, we need at least 1 week to discuss more about this particular object. If somebody is interested, just Google it first. In YouTube, you will find number of videos referring to Mandelbrot sets and sometimes Julia sets. So they are fractals formed by iteration in the complex plane. There is an advantage for fractal geometry. Fractal geometry is a culmination of all mathematics. I told you, fractal geometry is the mathematics of the universe. If someone asks you why you study mathematics, you can say to know the universe, to know this earth in a better way. Because even to discuss about a leaf, we need all mathematics. Because in fractal geometry, we need functional, we need analysis, we need linear algebra, we need statistics, we need differential equations, everything is involved in the study of fractal geometry. So everything together will tell you what is a leaf, what is the length of a leaf, etc., etc. So anyway, see, you can go and search this Mandelbrot set in the YouTube if somebody is interested, because our session is only for 1 hour. So now I'll tell you how to generate fractals mathematically. See, nature is filled with the fractals. All objects are fractals. But mathematically, there are several procedures. One such procedure is iterated function systems. Second is random fractals. See, when we take a glass of water, put some sugar inside, stir the sugar, these sugar particles will go here and there and will make the concentration uniform. So the trajectory of the Brownian motion becomes a fractal. Okay? And this is coming from differential equations. The solutions of certain differential equations are called strange attractors. They also form. See, look at this. These are solution spaces of certain differential equations. They also are fractals. And I told you in complex plane, iterations will give you fractals. So one by one we will see. I don't know how much we can proceed. First is iterated function systems. So you know what's a metric space. From the metric space, you take all compact sets. So in a bag, you have all compact sets. And the distance between two compact sets is measured by Hausdorff distance. There are some problems in the writing, so don't worry. You know the distance between two sets is measured as, if you want to find distance from a point to a set, you find the distance from the point to every member of the set and take infimum. And take the supremum. If you have two sets A and B, you take the supremum of such distances. If the sets are finite, of course, maximum and minimum will do. So the distance between two sets is defined using Hausdorff distance. So using Hausdorff distance, set of all compact sets in a plane or in a space or in a metric space becomes a metric space. That is called Hausdorff space. That is the space. Set of all elements in this universe, along with this universe, becomes a fractal space. H is a fractal space where all fractals live. Now, when you shrink an object, that is called a contraction mapping. You might have studied a little bit of function analysis. Contraction mappings, what they will do is, they will shrink the object. So distance between 2 points will be less than or equal to some number between 0 and 1 into the distance. That means they are shrinked. Smaller copies are taken. That smallerness, that factor is called contractivity factor. For example, look at this. F from R to R, f of x equal to x by 2. So that shrinks objects. Close interval 0 1 becomes 0 half in that manner. Okay. Now, this is a very famous theorem in mathematics, Banach's fixed point theorem or contraction mapping theorem, that says every contraction has a fixed point. Okay. If you start with a point in the metric space, and if you have a sequence, you take the iterations, f1x, f2x, f3x, etc., that will convert to that fixed point, irrespective of your selection. That's called Banach's fixed point theorem. That fixed point theorem can be applied in the space of mappings of, I told you about this, this fractal space. Then you take a metric space along with some contraction mappings, say S1, S2, Sm. So they all will have this shrinking factor, S1, S2, Sm. Its maximum is S. Then this set is called an iterated function system. X, S1, S2, S3, Sm. Look at this example. R, real line, S1x is x by 2, S2x, x by 3. So I will give more examples after some time. Now, the fractals are defined in this manner. If you take a metric space along with contraction, you define this map Hx, W from Hx to Hx defined as union of all these images, union in the first iteration. This is called Hutchinson mapping. This is a contraction mapping. If you take a compact set, find the squares, cubes for the sequence of images, that will converge to something that's called an attractor of the IFS. That will be unique. That will be a fractal. That's one technique to find. We will see some examples. Look at this picture. This is not a real. This leaf may be familiar to you. When we were all very young, we used to plug this leaf. We used to copy it on our hand. See, the white copy of this will be embedded in our hand. You may be remembering your childhood days. This is called Bensley's fern. This is a computer graphics image. In classical geometry, you cannot make this picture. But this is the picture. Mathematically, 1, 2, 3, 4, 5 contractions working continuously, iterating hundreds of times will create this picture. Okay. See how Condorcet works. This is how Condorcet works. You start with an interval, a line of length 1. Apply 2 mappings. Actually, Condorcet is obtained by removing the middle third, but it is not like that. You apply f of x equal to x by 3 to 0, 1. So you will get 0, 1 by 3 here. This is x of x equal to x by 3 plus 2 by 3. That's the second mapping. So you will get second interval. Again, apply both the functions here as well as here. You will get the next stage. Look at this. So f of x equal to x by 3 will give this. F of x equal to x by 3 plus 2 by 3 this. This. In that manner, it goes in this manner. Iterations will give you finally this Condorcet. So this 0, 1 along with f1 equal to x by 3, f2 equal to x by 3 plus 2 by 3 will give you this fractal Condorcet. Another example, Condorcet is some, you know the properties of Condorcets. Okay, that's a fractal, and the dimensions can be seen by using this box counting dimension. And this is a beautiful picture. This is the fractal Condorcet you obtain in 3 dimensions. You take a box, remove the middle volume, repeat the process. So there you may need more functions actually. You have to reduce the size, go to the left, go to the right, go to middle, so many functions required. Now, we are going to construct a fractal from a compact set in R2. This shaded region is a compact set in R2. I am applying 3 different three different functions one by one on this particular image. See, this is what is happening. When you apply S1 on the entire image, this is a contraction. This one shrinks and goes up. Look at this. This one, left, this lower triangle is the image. It is moved to left side. So when you apply second, see, look at this. Second function will take to the right side. Third to the top. When you iterate once again, same principle. Same. Iterations will lead you to the fractal. Actually, this fractal has no area, infinite length. So it is like our lengths. Our length is inside ribs. So finite volume, but infinite area. Infinite length, but finite volume. Let's look at this. We start with a square. Remove the square in the middle. Repeat the process. Mathematically, we are applying how many functions? 1, 2, 3, 4, 5, 6, 7, 8 functions are there. So IFS will be the square along with 8 functions. Iterate. You will get something like Sierpinski carpet. Okay, this is also a fractal. Now, its area is 0, but its length is infinity. You can easily show that. Now, area you can see it as 0. Of course, its dimension is 1.89. Okay, so it feels better than an area, right? There are so many wrinkles, crooks, bends. This is a 3-dimensional analog of that Sierpinski carpet. It's called Menger sponge. This is another one. How quest snowflake is obtained is actually mathematically an iteration is physically a transformation. You remove the middle third, then replace it by a V, a spike. This is the operation. Mathematically, you can define it. Repeat it once, twice, thrice. It goes like this. After infinitely or 1,000 or 1 million times, you will get like this. That one also is going like this, infinite length. If you have 6 flakes, you will get the real snowflake. Again, a beautiful fractal in the nature. Look at this. This is the starting seed. I treat. I am not specifying the functions here, but the operation is just rotate and do something. See what is going on after so many iterations. You will get this, a beautiful fractal called dragon curve or dragon fractal. Okay, I am leaving this actually, condensation mappings. See, suppose you want to, I'm not leaving, construct a tree. The trunk of the tree is common everywhere. But using trunk, you can create the tree. Reduce the trunk. Look at this. You start with this trunk. You make a smaller copy of the trunk. Place one on the left side, one on the right side, above this. This. Okay. So this is a constant everywhere. 2 transformations are applying. Look at this. That trunk is coming all the time. And the tree is developing. Look at this. So an IFS is producing a tree. Look at this. Trunk, tree is going to tree. So this cannot be produced in classical geometry. Only in fractal geometry using IFS we can produce this tree. Okay, this type of examples. Now so many examples, I'm not going to present each and every of the example. We are making new fractals, beautiful fractals. Anyway, yeah. A self-similar set, I already told you. When you produce fractals, see, let us proceed. Look at this fractal. This total fractal is union of its own copies. This copy, this copy, this copy. If you take a smaller portion, this side is copy of this, this, and this. So this is this. X is a metric space. A set is self-similar for a set of contractions if F is equal to union SIF. Its own copies are used to create the image. So Cantor set is self-similar. Look at this. And super self-similar. Suppose F is a superset of its own copies. The union is inside. That also is possible. See, if you start with a set, the union is inside actually. Such sets are called super self-similar set. If the union is, look at this. Anyway, the union is a subset of this. S1F, S2F, S3F union will be a subset of this. So that is called super self-similar set. There is something called sub-self-similar, that is F subset of union SIF. In this situation, it is called sub-self-similar. Examples, okay. There are several mathematical things. I'm skipping them because of time. We have only 5 more minutes to go. So iterator function system is one method to construct fractals. Okay. Now we will go to complex dynamics before we wind up. See, in complex plane, I told you already Mandelbrot set and Julia set. Consider a function from C to C such that f is z equal to z square plus c. Then Mandelbrot set is m equal to set a full constant such that, see, the orbit fn of is less than or equal to s. See, what are the constants for which the orbit of 0 is bounded? Okay, what are the constants for which the orbit of 0 is bounded? This is the function. What are the c's? See, set a full c in c so that there is a bound for which fn of 0 is less than or equal to s. See, c equal to 1, f1 0 1, f2 square, f1 square is 0. So you'll get an orbit z1 2 5 26. It is escaping to infinity. This 1 is not in the Mandelbrot set. Look at this. This is it. If you take a -1 here, its image will go to infinity. But if you take a point here, f of z equal to z square plus, what are the constants for which the orbit of 0 is bounded? So these black or shade points are those points for which the orbit of 0 is bounded. So these are not points, these are the constants. So this is the parameter space, c values for which fz equal to z square plus c is orbit for 0 is bounded. That will create a shape in plane, and its boundary is a fractal. Okay, so the object we are obtained is M. It's symmetric about the real axis. If Z is in M, Z bar also is in M. So many mathematical properties. M is compact, M is connected. See, this picture is obtained using coloring algorithm. Suppose a point moves to infinity in a lower speed, they will be in the yellow region. Suppose they form very quickly, say 2, 24, 1 million, then that will be in the red portion. So depending on the speed of their divergence or convergence, we give these colors. So coloring algorithm is used. So these black points, their orbits will be bounded, orbit of 0, for the which are the constant C, for which f of z equal to z square plus c is bounded. Okay, so that is Mandelbrot set, and sometimes called the filled Mandelbrot set. Their boundary is actually called the Mandelbrot set. Okay, just a second. I have a very important call. I'm coming. Okay, so see, this is a very famous fractal actually. Look at this. Coloring algorithm is used to produce beautiful fractals, okay, using complex dynamics. See, and now there is a beautiful thing actually related with this. You fix one C, okay, f of z equal to z square, for example, or f of z equal to z square plus 0.25, for example. Find the value, find the z's for which their orbits are bounded. They are called Julia sets. Okay, this is Mandelbrot boundary of Mandelbrot set fractal. That is why this is important to us. Very important fractal. We are not discussing it. This is the first fractal we develop using complex dynamics. Now, this has topological dimension 2, whereas its Hausdorff dimension also is 2. It's a very, very important fractal. If somebody interested, they can read it and study very nicely. Now, Julia set is an important thing. The set-fold Z for which f and z is bounded. You fix an f, find the orbits of a number under the function. See, f of z equal to z square plus z. Okay, I'm putting C as 0. So it is very clear that for all mod z less than 1, f z equal to z square will converge. If mod z greater than or equal to greater than 1, it will go to infinity. Mod z equal to 1, it will be bounded. So this is the Julia set. You will become absolutely, see, look at this C equal to -1. This is the Julia set we develop. Beautiful. Beauty is just to come. See what a beautiful Julia set it is. See, this can be produced in the plane with a computer. Till 25 or 30 years, it was not possible. Why? Computers were not available. A mathematician was unable to see the beauty of this picture. So that is it. So with this complex number, what are the sets for this C whose orbits, powers, f of z naught, f square of z naught, f cube of z naught, etc. are bounded? This black shaded region points belongs to that category. Outside, depending on the speed, several colors are given. So, look at this picture actually. Beautiful, indeed beautiful. So, only the computers now show us the beauty of Mandelbrot set. Look at these jasmine type flowers. This belongs to another. See, it's wonderful. It's a beauty of, it's a divinity of mathematics. Look at this again. For different constants, you will get different Julia sets. So beautiful fractals can be found by complex dynamics. Beautiful complex dynamics. You just refer to Google and search, you will find infinitely many pictures. Okay, so Julia set also sometimes called filled Julia set. The boundary becomes a fractal. These are the fractal boundaries of the Julia sets. They have several important applications in different equations and all. So these are the properties of Julia sets. Jeff compact, boundary is compact, chaotic, so many. Chaos theory also will come in between. So look at this. For a Mandelbrot set, if you take a constant here, correspondingly, this is the Julia set. If you take a constant here, this is the Julia set. This is the Julia set. So beauty of mathematics is in fractals. Remember, we need all subjects in mathematics, starting with analysis, ending with I don't know. Even with all the available math, you cannot study this universe. Okay, it has plenty of applications in all fields of science and technology. So the initial problem I told you, now there is a transform called a fractal transform that will reduce the size of a picture by removing the self-similar portions. So if I have to send you a 10 GB image, I will reduce the self-similar portions. I'll send you 1 KB image. But at your computer, you will use the inverse fractal transform and recreate the image in its original shape. That is the application of fractals. That is why I told you about James Webb telescope. James Webb is using fractal transform to compress it and send to this Earth. In Earth, we will recover it using fractal transform. Each and every topic I mentioned here needs more explanation. I know that, so that they will do in future. But if at least one among you becomes interested in fractals, please come forward and contact me. I will help you in your research. Where if you're interested in functional analysis, we will do research in function analysis with fractals. Topological side, differential side, statistical side. Whatever we want, we can do it in fractal geometry. So many applications in engineering. Okay. See, this is a fractal antenna developed better than classical antennas. It was in 2002. Okay. So we have done a lot of work. My scholars, Ranju, Ashwadi, many, they have all done beautiful and wonderful works in the past. And if somebody is interested in doing research in fractals, please contact me. And I'm going to wind up this. Now it is up to you. If you have any doubt, you can ask me your doubts. Okay? Yes. Thank you. Actually, when I speak to a computer, I don't know whether I have audience in front of me. Are you all there?
Yes, sir.
Yes, thank you. So it is your question time. If you have doubts related with this discussion, please come forward.
Yes, sir.
Any doubts? Any questions?
Sir, no queries, sir.
Pardon? No queries.
Yeah, sir.
Okay, then thank you. Let us wind up the session. So read more on fractals, get fascinated by the fractal world, do research in fractals.
Thank you, sir.
Okay? Try to do some research on fractals. If somebody is interested, contact me.
Thank you, sir, for intellectual informative talk to various applications. Now, I'd like to invite Mr. Q. Mumimali, Assistant Professor, PG and Research Department of Mathematics, SFRC, to deliver the vote of thanks.
Good afternoon to Nadar present here. It is my great honor and privilege to extend the vote of thanks to our esteemed resource person, Dr. Sunil Mathew, Associate Professor, Department of Mathematics, National Institute of Technology, Calicut, Canada, who graced us with his expertise on a captivating topic of iterative function systems and factors. His illustration of this session has left an intelligent mark on our understanding, igniting curiosity, and fostering deeper insight into the intricate world of mathematics. Sir, your global knowledge and passionate delivery have captivated our minds and inspired us to explore further fascinating reactive factors and iterative function systems.
Also, I would like to extend my gratitude to all the participants who actively participated in this session. Thank you once again. Thank you, ma'am.
Okay, thank you. Thank you very much.
Can you wind up the session, sir? Thank you all, except AJ and SFR College.